Placing the higher leg on phase B in panels helps balance the loads more evenly across all three phases. This is because the majority of single-phase loads are connected to phase C, while three-phase loads are often connected to phases A and B. Some equipment, such as lighting ballasts and transformers, may be designed to operate on specific phases. By placing the high leg on phase B, it ensures compatibility with these devices. The utility meter is designed to measure the voltage difference between the high leg, which is phase C, and the neutral. Placing the high leg on phase C ensures accurate voltage measurements. Some utilities may have specific requirements for the placement of the high leg in the meter base. It's important to follow these regulations to avoid any issues with the billing or service. If the high leg is not placed on phase C in the meter base, the utility meter may not accurately measure the voltage, leading to incorrect billing. Incorrect placement of the high leg can cause damage to equipment that is not designed to operate on the incorrect voltage. If a load is connected to the high leg through a neutral connection, for example, a light fixture with a hot and neutral connection, a short circuit can occur, posing a safety hazard. Therefore, it is important to follow the established practices and utility regulations to ensure the proper placement of the high leg on both phase C in the meter base and phase B in panels. A 120V/240 volts delta service, often referred to as a three-phase, four-wire open delta system, is a type of electrical service that provides both single-phase and three-phase power. This configuration is commonly used in commercial and industrial settings where there's a need for both 120 volts for lighting and small appliances and 240 volts or higher for larger equipment. The term delta refers to the shape of the transformer windings in the system, resembling the Greek letter delta. In a 120V/240 volts delta service, three transformers are connected in a delta configuration. Two of these transformers are center tapped, providing 120 volts on each side of the center tap and 240 volts across the entire winding. The third transformer is not center tapped and provides 240 volts. The center tap of one of the transformers is grounded, creating a neutral point for the system. This grounded neutral allows for 120 volts single-phase power to be derived from each of the center tap transformers. The voltage between one of the phases, such as phase B and the neutral, is higher than the voltage between the other two phases and the neutral. This higher voltage is commonly referred to as the high leg, wild leg, stinger leg, or bastard leg. The high leg voltage is typically around 208 volts in a 120V/240 volts delta system. The high leg is a result of the delta transformer configuration and the way the neutral is derived from one of the transformer windings. It is essential to identify the high leg to avoid connecting 120 volts equipment to it, as this can cause damage. The National Electrical Code, or NEC, requires that the high leg be identified by an orange color. This can be achieved by using orange-colored electrical tape or orange-colored conductors. The NEC also requires that the high leg be placed in the B phase position in panel boards and other distribution equipment. This helps to ensure that electricians and other qualified personnel can easily identify the high leg. The high leg is typically used for three-phase loads, such as motors and 8-track equipment. These loads require a balanced three-phase power supply, and the high leg provides the necessary voltage and current. Single-phase loads can also be connected to the high leg, but it is important to ensure that the voltage is compatible with the equipment. In some cases, a buck-boost transformer may be required to reduce the voltage to 120 volts. When working with a 120V/240 volts delta service, it is essential to follow all applicable electrical codes and safety procedures. Only qualified personnel should work on electrical systems, and all work should be performed with the power off. Before working on any electrical equipment, always verify that the power is off using a voltage tester. Wear appropriate personal protective equipment or PPE, such as safety glasses, gloves, and insulated tools. Never work alone, and always have a qualified person nearby in case of an emergency. If you are not comfortable working on electrical systems, contact a qualified electrician. Firstly, meter accuracy is essential. Utility meters are specifically designed to accurately measure voltage. They are set up to account for the voltage difference between the high leg, which is phase C, and the neutral connection. Maintaining this specific placement guarantees the meter's readings are accurate, which is crucial for correct billing. Secondly, there are regulatory considerations. Utility companies often have strict guidelines about where the high leg should be positioned within the meter base. These guidelines are not arbitrary, they are in place to avoid billing issues and to ensure the service operates correctly. Following these regulations helps maintain the integrity of the electrical service. Thirdly, incorrect placement leads to inaccurate readings. If the high leg isn't correctly placed on phase C in the meter base, the meter may not accurately measure voltage. This inaccuracy can directly lead to incorrect billing, causing financial discrepancies for both the utility and the consumer. Fourthly, the risk of equipment damage increases. The high leg provides a higher voltage than standard circuits are designed to handle. Incorrect placement of the high leg can result in damage to equipment that isn't built to withstand the excess voltage. This could mean costly repairs or replacements. Fifthly, there are significant safety concerns. Connecting loads to the high leg via a neutral connection can create a serious safety hazard. For instance, if a standard light fixture is improperly connected, it can lead to a short circuit. Such a scenario poses a safety risk for anyone nearby. Sixthly, load balancing becomes more effective. Placing the high leg on phase B within panels is beneficial for distributing electrical loads more evenly across all three phases. This strategic placement takes into account that most single-phase loads are connected to phase C, while three-phase loads are typically linked to phases A and B. Seventhly, equipment compatibility is ensured. Various types of equipment, including lighting ballasts and transformers, are engineered to function on specific phases. By consistently placing the high leg on phase B, compatibility with this equipment is maintained, ensuring that devices operate as intended. Eighthly, adherence to safety standards is paramount. It's crucial to follow all established practices and utility regulations. This ensures that the high leg is correctly placed both on phase C in the meter base and on phase B within the panels. Following these guidelines helps avoid voltage measurement inaccuracies, protects equipment from damage, and ensures a safer electrical system. Ninthly, understanding three-phase power systems is vital. The 120 volts/240 volts delta service is a common setup in commercial and industrial settings, providing both single-phase and three-phase power. The delta configuration of the transformers allows for a high leg voltage, typically around 208 volts in this setup. Tenthly, identifying the high leg is critical for safety. The National Electrical Code requires that the high leg be marked with an orange color to prevent accidental connections to equipment not designed for that voltage. It also mandates that the high leg be placed in the B-phase position in panel boards. The purpose of the high leg, or wild leg, in a 120 volts/240 volts delta electrical system is multifaceted, serving to optimize load balancing, ensure equipment compatibility, and facilitate accurate voltage measurement. A high leg, typically registering around 208 volts, is a consequence of the delta transformer configuration used in the system. Its presence is not arbitrary, but rather a carefully engineered aspect of the power distribution network. One of the primary reasons for the high leg's existence is to enhance load balancing across the three phases of the electrical system. In a 120 volts/240 volts delta system, single-phase loads are commonly connected to phase C, while three-phase loads are connected to phases A and B. By strategically placing the high leg on phase B within panels, engineers can distribute the electrical load more evenly. This distribution prevents any one phase from becoming excessively burdened, which could lead to voltage imbalances, overheating, and potential equipment failure. A balanced load ensures that the system operates efficiently, minimizes energy waste, and prolongs the lifespan of electrical components. Equipment compatibility is another crucial factor in determining the high leg's placement. Certain types of electrical equipment, such as lighting ballasts and transformers, are designed to operate on specific phases. By consistently placing the high leg on phase B, compatibility with these devices is maintained. This standardization prevents misconnections that could result in equipment malfunction or damage. Moreover, it simplifies the installation and maintenance processes, as electricians can rely on a consistent phase arrangement. The utility meter's accuracy is also dependent on the correct placement of the high leg. Utility meters are engineered to measure the voltage difference between the high leg phase C and the neutral connection. This measurement is essential for accurately determining the amount of power consumed by a customer. If the high leg is not correctly placed, the meter may not provide accurate readings, leading to billing discrepancies and potential disputes between the utility and the consumer. By adhering to utility regulations and established practices, the integrity of the voltage measurement is preserved, ensuring fair and accurate billing. Moreover, the correct placement of the high leg is critical for safety. Misconnecting loads to the high leg can create hazardous conditions, particularly if a neutral connection is involved. For example, if a standard light fixture is connected to the high leg through a neutral connection, it can result in a short circuit, posing a risk of fire or electric shock. To mitigate this risk, the National Electrical Code or NEC requires that the high leg be identified with an orange color and placed in the B phase position in panel boards. This standardization helps electricians easily identify the high leg and avoid accidental connections. The 120-volt/240 volts delta service is a common power distribution system used in commercial and industrial settings. It provides both single-phase and three-phase power, making it suitable for a wide range of applications. The delta configuration of the transformers allows for a high leg voltage, which is typically around 208 volts. Understanding the purpose and proper handling of the high leg is essential for anyone working with this type of electrical system. In summary, the high leg in a 120-volt/240 volts delta electrical system is strategically placed to optimize load balancing, ensure equipment compatibility, facilitate accurate voltage measurement, and promote safety. Its presence is a testament to the careful engineering that goes into designing and maintaining electrical power distribution networks. By understanding the purpose and proper handling of the high leg, electricians and other qualified personnel can ensure the safe and efficient operation of electrical systems. Firstly, it is used for load balancing. Placing the high leg on phase B in panels helps to distribute the electrical load more evenly across all three phases. This is because the majority of single-phase loads are connected to phase C, while three-phase loads are often connected to phases A and B. Secondly, equipment compatibility is key. Some electrical equipment, such as lighting ballasts and transformers, are designed to operate on specific phases. By placing the high leg on phase B, it ensures that this equipment is compatible and can operate correctly. Thirdly, meter accuracy is crucial. Utility meters are specifically designed to measure the voltage difference between the high leg phase C and the neutral connection. This placement ensures that the voltage measurements are accurate, which is essential for accurate billing. Fourthly, utility regulations play a role. Utility companies often have specific requirements for the placement of the high leg in the meter base. Following these regulations is important to avoid issues with billing or service. Fifthly, the consequences of incorrect placement can be severe. If the high leg is not placed on phase C in the meter base, the utility meter may not accurately measure the voltage, which can lead to incorrect billing. Sixthly, equipment damage is a concern. Incorrect placement of the high leg can cause damage to equipment that is not designed to operate on the incorrect voltage. Seventhly, safety concerns are paramount. If a load is connected to the high leg through a neutral connection, it can create a short circuit, posing a significant safety hazard. Therefore, it is crucial to follow established practices and utility regulations to ensure the proper placement of the high leg on both phase C in the meter base and phase B in panels. The 120-volt/240 volts delta service is a type of electrical system commonly used in commercial and industrial settings. It provides both single-phase and three-phase power, making it versatile for a wide range of applications. The term delta refers to the shape of the transformer windings in the system, resembling the Greek letter delta. The high leg is a unique feature of this type of electrical system. The voltage between one of the phases, typically phase B, and the neutral is higher than the voltage between the other two phases and the neutral. This higher voltage is typically around 208 volts. The National Electrical Code (NEC) requires that the high leg be identified by an orange color. This helps to prevent accidental connections to equipment that is not designed to operate on the higher voltage. The NEC also requires that the high leg be placed in the B phase position in panel boards and other distribution equipment. This standardization makes it easier for electricians to identify the high leg and avoid potential hazards. When working with a 120 volts/240 volts delta service, it is important to follow all applicable electrical codes and safety procedures. Only qualified personnel should work on electrical systems, and all work should be performed with the power off. Before working on any electrical equipment, always verify that the power is off using a voltage tester. The high leg in a 120 volts/240 volts delta electrical system is intentionally placed on specific phases to optimize load balancing, ensure equipment compatibility, and facilitate accurate voltage measurement. This configuration is carefully engineered to provide a safe and efficient distribution of electrical power.